Good afternoon, RSM freshmen. Here's another video lecture for you. Today we're going to be talking about our second section. This will be the rates that chemical reactions occur in, and mainly what affects the rate of reaction. So let's go ahead and get started. Now, to clarify, the rate of reaction is the rate at which the concentration of products increases or the concentration of the reactants decreases. Either one will work. For the most part, what you're looking at is over time, concentration of products will increase or the concentration of reactants will decrease. Either one of those can be measured over time. That is the rate, kind of like miles per hour, say distance over time. Okay, that's not the only way that rates can be done, but this one we'll be talking about time. So, in order for a reaction to occur, the reactants must have enough activation energy, and this is going to be marked by a EA. So EA, or the activation energy, is the minimum energy required to overcome the energy barrier for a reaction. So for every chemical reaction, there is a certain amount of energy that has to be overcome in order for the reactants to exchange partners, and for the most part, in order for new products to be formed. Okay, so there has to be a certain amount of energy that has to be achieved by the substance or substances in this case to produce new products. Okay, that is called activation energy. So now, best way to gain activation energy, we're right here now. Okay, the best way to gain activation energy is to increase the particle's speed or their kinetic energy, E of K. Now, when we talked about, and we'll talk about a little bit more in second semester, but there are really two main types of energy. There is kinetic energy and there is potential energy. So to increase kinetic energy, which is the energy of motion, okay, we'd have to do a couple of different things, which we'll get to in a second, to do that. But that's really what we're going to try to do, is to increase the kinetic energy, which should increase the force in which the reactants come into contact with each other. So that's the main goal of adding kinetic energy. So kinetic energy is used to break the bonds between the reactant atoms to form new products. So here's a graph that kind of shows what we're describing here. So here I have circled the reactants, and you notice they're kind of in a flat line right here. On the y-axis, we have free energy. So this is really talking about the total amount of energy in the system. Okay, the reactants right now are being held at this amount of energy. This graph was measured in, I would assume, joules. Okay, so the potential energy is stored by the reactants is marked by this line right here. It's circled for you. Okay, you can see the term activation energy again is the minimum energy required for a reaction to occur. All right, this circle right here talks about the energy required for the reaction to actually take place. So in this case, this point right here, this transition state that it's pointing to, this is the energy required for the reaction to take place. And then, of course, you see this long plunge where the system is losing energy, and of course, we have our products. Now, a little helpful tip for you, or not helpful tip, or a question for you, if you could, think about and maybe come up with a piece of evidence for what type of reaction this would be. Would it be endothermic or exothermic, based on the idea that it's losing energy and its products have less energy than its reactants? Okay, so anyway, getting back to the original graph. In this case, the reactants have to gain energy. They have to add energy to the potential energy they already have. They have to add energy, and the way that we're going to do that is through kinetic energy. We have to raise that energy in those substances just enough so they can hit that activation energy point. After we get to that minimum energy, the particles will then start to react, and then we will end up having the reaction occur, and then we'll actually start losing energy. Sorry about that. And our products will actually end up with less energy. Now, this isn't a graph for all chemical reactions. You could imagine that different types of reactions, as far as whether they're taking energy or releasing energy, will look a little bit different. But again, I asked the question before, which type of reaction would this be? Would this be endothermic or exothermic? All right. So now we're talking about the rate of reaction, we're talking about having to hit this activation energy. Well, what are some ways that we can increase the reaction rate? Okay, so for the most part, we have three ways. The concentration of the reactants can be increased. Okay, so that's just like adding more wood to the fire. The reaction will increase. The absorption of energy, two ways that we can absorb more energy. Either we can increase the temperature, increasing kinetic energy, or we can take in more electromagnetic radiation, or what's simply known as light. Okay? And the third way that we can increase the rate of reaction is, of course, the introduction of a catalyst. So what we're going to do here first is talk about the concentration of reactants. So reactions occur if the reactants come into contact with each other. So I have a little diagram here I took off the internet. These are the two reactants, nitrogen gas and oxygen gas. Notice here they're diatomic, N2O2, those are diatomic elements. Okay, nitrogen gas and oxygen gas. These are free floating, and you see this little kind of almost like fade away here of the actual picture. That's supposed to be depicting, motion. So these particles are actually moving towards each other. And it is important that the particles hit at the right angle, so on and so forth, so they can't just be glancing off of each other. They actually have to hit at a certain part in order for the reaction to occur in the exchange of their particles. Okay? So anyway, these particles come together. Then the reaction upon colliding will occur and will actually end up with a new product, which is NO, or nitrogen monoxide, as it's said here. So that's kind of what we're shooting for in a reaction. We have to have our reactants come together in order to form new products. Okay, so it's only logical then that if you increase the amount of reactants, the rate of reaction will become faster because of an increase in potential collisions. Okay, so I have two containers here. Same amount of green liquid within them. Experiment 1, experiment 2 holds the same amount of green liquid. Which one would you suspect would have a greater concentration of reactants? Correct. Experiment 2 would have a greater increase. And why is that? Well, look at this, the reactant here, this green, baby poop green circle. Okay, that's meant to be a reactant that can, of course, move down and through. Come on, computer. Move down and through and start a reaction here. Okay, so what we're shooting for, as far as understanding is concerned, is that we want you to see that a greater concentration of reactants will actually cause this reaction to occur faster, okay, or increase the rate. Now, there's not a real problem with this, but this assumes, of course, that the particles have enough energy for the reaction already. So this is assuming that these particles are already moving fast enough that the reaction will occur the way we need it to occur. Okay, so the biggest thing when we talk about reaction rate and we talk about chemical reactions in general, you're talking about the activation energy. Okay, so for us, when we're talking about the concentration of reactants, we can go ahead and throw more logs on the fire. But if you just throw logs onto logs, well, there's no reaction occurring. So there has to be enough energy already in the system for the reaction to occur. Okay? So then this kind of moves us to our second method of increasing the rate of reaction, and that's the absorption of energy. Again, we talk about two ways. The first way is the electromagnetic radiation, the light, and we talk about the light spectrum. There's ultraviolet light, there's infrared light, all those different things. But for the most part, we're talking about light, and so you're talking about wavelengths of light, visible light if you want it to be, of course. The absorption of light by reactant molecules helps the atoms vibrate more violently. So you can think about these molecules that are inside or that are in the substance itself, catches the light, it excites their electrons enough that they begin to vibrate. Okay? That vibration will increase the energy of the reactants, and will actually break the bonds between the atoms. So you can think about these little circles vibrating, 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 and all of a sudden they have enough energy they just break apart. Okay, so that's what light does. Now, light is an important factor in photosynthesis. When we talk about photosynthesis, we're talking about light energy coming in and exciting electrons. Okay, and we're talking about an electron transport chain, which creates an end product. Okay, so that's a very simplified version of what it actually does, but it creates this electron transport chain, which will eventually create other forms of chemicals which can store energy, which are eventually used to create sugars for the plant. Okay, so now that's the way that electromagnetic radiation or light can be used. Now that's not the only way, but I mean, you can talk about atmospherically. There's lots of things that absorb light and can go through the reaction using just light as a form of absorption of energy. When we talk about temperature, which is probably a little bit more common in your world as far as how reactions occur and how they can increase, but if you increase the temperatures, it means the particles will move faster. So temperature, we haven't really talked about temperature all that much, but temperature is really just a measure of how fast particles are moving. Okay, so if particles are moving faster, they'll have more kinetic energy. Okay, that's if they're moving slower, then they have lower kinetic energy. That's kind of how that relationship works. So the increase, this increase increases the force of collisions. Okay, so it increases the chance that the bonds are going to break. So that's a very important part. If we can get the particles moving faster, that'll increase the amount of force that they're going to have. Okay. So living organisms follow that same type of rule. So we have, of course, endotherms, which the body temperature remains relatively constant and allows reactions to occur on warm days and cold days. So there's a nice picture of a horse kind of jumping there. Its reactions can occur because it maintains its own body temperature. Okay, it doesn't rely on the outside temperatures in the atmosphere to dictate its chemical reaction. So that's an endotherm. Of course, on the back side of that would be an ectotherm. Okay, this is where body temperature is regulated by outside temperatures. So these would be like snakes and more likely a reptile. Okay, so on warm days they're very active. Cold days they're pretty lazy. So if you're ever going to walk through a swamp, you'd want to walk through on its coldest day, on its cloudiest day, because this is when the alligators, of course, would be at their weakest. So that's kind of an important deal. But for the most part, ectotherms use outside temperature, not very reactive on cold days. An endotherm would be self-regulating and thus allows reactions to occur at any time. So now, what we're probably most concerned about now, after we've talked about, okay, substances increasing, we've talked about absorption of energy, whether it's through light or through temperature, we got to think, okay, there's got to be something easier than maybe I'm not around a temperature changing device such as fire or a heater of some sort, or I don't have any more substance. Okay, so what can I do? Well, the third way that we can increase the rate of reaction is to, of course, introduce a catalyst. Okay, so a catalyst is a substance that increases the rate of chemical reaction by lowering the reaction activation energy. Okay, so we're putting an S in there also. Catch fire for that. Anyway, but by lowering the reaction's activation energy. Remember, the activation energy is the minimum energy required by the particles of the substance in order for a reaction to actually occur on its molecules. Okay, so if we introduce this catalyst, it will actually lower that activation energy. So I'll have a graph here in a second that talks about lowering the activation energy. But when we talk about a catalyst, they're never used up in a reaction. Thus, they're available throughout the reaction for more breakdowns. A good example of what a catalyst does would be like a nut and a bolt. They're rusted together, let's say. If we wanted to get that nut off of the bolt, we would use a tool. This would be a wrench, a crescent wrench, any other a standard stationary wrench as well. But that wrench makes the amount of energy that we would have to use to take that nut off the bolt, it lowers it. So we don't have to use near as much energy to do that. So a wrench, very commonly, is a catalyst because it lowers the activation energy. And more importantly, at the end of using that, breaking that nut off of that bolt there, you don't throw the wrench away. Okay, yeah, it can be used again for other things. Okay, so for the most part, that's how that's going to look, and that's how it's going to work. So this is what we're going to do. See, I forgot to put this in here. Let's go and insert a picture. Okay, this picture is referring to a catalyst. Okay, so you can see it's a very similar type of graph to what we saw initially. We have energy on our y-axis, and then the reaction going down here. All right, so we see it's a similar type of reaction. We see that the reactants hold a certain amount of potential energy. Our products don't hold that near as much energy, so it's actually releasing energy. This would be an exothermic reaction, going back to the original question about this graph. Okay, so now you can see we have two lines here. We have a red line and we have a blue line. Okay, this red line actually represents the amount of energy that would be needed to gain by these products, carbon dioxide and water, to produce, this would be carbonate over here. Okay, so carbon dioxide and water actually would need to gain this much energy as a substance. Now, there's two ways, or one major way that they can gain that energy is that through kinetic energy, which we could increase by temperature, or if these two want to gain light energy, they can do that as well, okay, for the most part. So this is what they would need. Now, this graph shows another blue line here, okay. The potential and the ending energies are the same because they're stored in these molecules, but the amount of energy you can see is lowered, okay. The size of the hill, if you would like to call it that, has been lowered. So the activation energy, and this is talking about an enzyme, so these would be, an enzyme is a biological catalyst, okay, these things are in your body. DNA synthase would be one. Catalase is an enzyme that breaks down hydrogen peroxide in your body, produces oxygen and water. But you can see that this catalyst, okay, which is what this graph is talking about, lowers the activation energy. So by lowering the activation energy, the rate of reaction occurs faster because there's less energy, there's less of a hill to get over in order for that reaction to occur. Okay, so that's basically how these things will work. So that's kind of the end of the presentation as far as what we're talking about and what we're trying to get across here. So remember, the main things that we're talking about here are ways to increase the rate of reaction. So you're talking about, to increase the rate of reaction, you have to first get over the activation energy hump. Okay, in order to do that, you have to increase your kinetic energy. All right, there's a few ways to increase the reaction rate. One is the concentration of reactants. Second way is the absorption of energy, which is probably the main way. You talk about temperature increases or the electromagnetic radiation. And then third way, and the more convenient way in a lot of ways, is the introduction of a catalyst. In your body, it's called a enzyme, and in normal chemistry type terms, it's a catalyst. Okay? So go ahead and proceed and work on your study guide. Thank you for working quietly. Thank you.